Hello, and welcome back to Human Evolution. Today I want to talk about geologic time. We have a planet that is 4.6 or so billion years old, and we've divided time since the beginning of, Earth time into all sorts of divisions. And so when we talk about geologic time, we're talking about these very long periods of Earth's history. And there are two ways to do it. We talked about this when we talked about fossils. There's relative time, which is placing events in sequence, right? And then there's chronologic, right, order, and that is where you determine the actual age of something or the actual time of a particular event. Okay? Now, when we talk about geologic time, we want to talk about the geologic time scale. And so this is based on fossils, and part of this is about index fossils. You'll find certain animals only in certain periods, or you'll find an abrupt change in body types or places like habitats, all kinds of like land animals versus aquatic animals. And when you start dividing this out, you can see that you have this very long period of time. And this is really not drawn to scale, by the way, because this is 4,500 million years, right? Whereas this is 65 million years. Okay, that's a huge difference. You're talking about a billion-year difference right here. So obviously this is not drawn to scale. But anyway, so you have all of this early time. Life evolves right here at the end of the Hadean. We move into the Archean. And so you have all of this very simple, slow life going on. Then, right around 540 million years ago, we have what's called the Cambrian explosion. And when we are talking about things that are important to the evolution of humans, right, there are lots of things that have happened in this area right here. But the majority of things that we want to talk about will have happened since that Cambrian explosion. And the Cambrian explosion is called that because all of a sudden you have this massive adaptive radiation. And adaptive radiation is something we'll talk about again. But basically what happens is you have all of these empty niches, and animals evolve at a very rapid pace filling these niches. That's what's going on. Okay? And so we're going to be dealing mostly with this part of the geologic time scale. Okay? And so when you look at, here's the Cambrian, right? This says 470. There's debate about when each of these things came up. But basically, the Cambrian begins with the earliest of the shelled animals. And you can see the Cambrian to Ordovician fish marks that. So this is the age of fish. Then you get your land plants in the Silurian, right? Then you get your amphibians towards the end of the Devonian. Then you move into the Carboniferous because you have these large land plants. The Pennsylvanian, by the way, is also when you get your coal-forming swamps. And so we just move on from there. And then here is the last. This is where the dinosaurs show up, right? And so we go all the way up to here. This is the Cretaceous, the KT boundary, right? And that's the Cretaceous to Tertiary period. That's that boundary. And so this is where we're having all sorts of mammal evolution going on, right? And then in the Pleistocene, these are where you find the earliest humans. And so the age of humans actually begins right here. The Pleistocene epoch is the first part of that, and the Quaternary period is where we live. And we'll come back to this over and over and over again. But this is just to give you kind of like an overview. And then here's another one, right? And you can see that there are different ages. And so like when you talk about the Cambrian, this is 545. We've seen 540. We saw 570. 570 is not awesome in terms of the dates. It's really around 540, 545. But anyway, so here's all of those things put together. And so I want you to kind of have an idea of the order of things. And we'll talk more later about the ages, right? So you have the age of invertebrates, age of fishes, age of amphibians. Oh, fishes, by the way, fish is like one fish. Fish can also mean like 5 fish. But when we say fishes, we're talking about multiple species of fish. Yeah, multiple groups. Okay, so here's your first question. There's no disagreement about the divisions of time. That is totally false. We just saw an example of that. Okay, so let's talk about the continents. Part of what we see in the world, the ecosystems, the animals, all of these, the plants, all of this, has a lot to do with where the continents are. And the continents have moved a lot over the last, several hundred million years. And so we're going to start with the Silurian. And the Silurian world looks something like this. And you have this massive Gondwanaland, and you can see the modern continents and where they are. But here's North America, and here's Europe and Siberia, and so they're like equatorial islands. That's pretty exciting. And then everything else is kind of down here in the Antarctic, or wrapping up around. This is all equatorial too. That's pretty exciting. But you don't have the large continents that you have up here like you have today. Anyway, so next thing, as time passes, okay, you move into the Devonian, and you can see these have actually moved a lot in this 20 million year period, right? And you get Laurasia. All of these guys were converging into this big continent. And then by the time you get to the Mississippian, you can see that we're starting to form this big supercontinent. But right now we've got the Gondwanaland, which is one, and Laurasia are coming together. These two supercontinents are coming together. And eventually, by the time you get to the Permian 250 million years ago, you've got this single continent called Pangaea. And we'll talk about that later on, because at this point, everything's connected. So any life is able to go from one place to another. And this goes back to that idea of the fossils that we find across continents. This is how that worked. Okay, and then we move on. Pangaea starts to break up around 200 million years or so at the Triassic, and then we move back into Laurasia and Gondwanaland. And then by the Cretaceous, we see the earliest of the continents that we're going to see later on. But you can see India's down here, so is Australia. They're going to start moving north. Remember, India is going to slam up into Asia later on. And so by the time you get to the early Cenozoic, not too far after the dinosaurs have gone extinct, you can start to see the modern world forming, but India still hasn't made it. There's no Himalayas or anything like that. They're relatively new. Okay, so continents are in their final positions now and remain there. So what that statement is saying is that we've reached the max of the movement, and everything is where it's supposed to be. That is totally false, because there's no place that everything is supposed to be. Everything is still moving. And remember from our fossil conversation that the Atlantic gets wider by almost 3 centimeters a year. Okay, now let's talk a little bit about some evolutionary milestones. We've talked about some of them, but it's very important to understand that the theory of evolution is fundamental to everything that we know about biology. The idea and evidence for evolution existed well before Darwin, but Darwin was the one to really solidify some of these ideas, and we'll get back to that later on when we talk about natural selection. But the bottom line is this. Geologic time and understanding geologic time is very important, because it takes billions of years for things to change, because organisms change slowly, and so it takes a long time for that to happen. Now, some of the evolutionary milestones that you need to understand are really important are some we've already talked about. We talked about multicellularity, tissues, bilateral symmetry, body cavities, and we're going to take the body cavities one step further, and that's into the coelom. And the coelom is a body cavity in between the mesoderm and the endoderm, the gut, that arises from gastrulation. Okay, and that was something that we talked about. Now, it turns out that there's some other really important things too, like segmentation. When you think about segmentation, it's often easy to think about something like this, where you have this little, lobster, crawfish guy who's got all these body segments, or an earthworm or whatever. But if you look at us, we're segmented too. That's pretty exciting. Jointed appendages, right? Legs, helpful, yeah? Deuterosomes, deuterosomes are animals who have a mouth that forms from something not the blastopore. And as a matter of fact, deuterosomes, the blastopore forms the anus, really. And so the mouth is formed from a totally different cavity that joins the digestive tract later on. So we happen to be deuterosomes. So then notochord is really important. This is the spinal cord, right? Now, ours is protected in this lovely segmented piece here called the vertebral column. And so there are some animals that do not have vertebral columns. They're not vertebrates, right? But notochord, this central nervous system, really important, really significant. Next thing is sexual reproduction. Sexual reproduction occurs early on in the evolution of life, about 1.8 billion years ago. Now, 2 billion years after life evolves, but it's still a long time ago. The great thing about this is you get this wonderful variety, because you have these 2 different parents, you have recombination. It's great. Okay, sexual reproduction results in new genes in a population. True or false? That is false. Mutations are the only way to get new genes. Sexual reproduction allows for a different combination of genes, which is very helpful and can give rise to new traits. Okay. Now, about 430 million years ago is when you start to see land plants and animals, all right? And that's really important to us because we are land plants and animals. Reptiles evolve on land, mammals evolve on land. And when you start looking at some key things, first vertebrates, they're the first bony fish. We have bones, we like that. The first reptiles, we're going to evolve from reptiles. Tetrapods are also interesting because 4 legs is helpful. We walk on 2, but we have 4 limbs. But so the first reptiles, and then I just talked about the tetrapods. The first mammals, right? Again, we're evolving from reptiles. The first birds are fun because they actually evolved from dinosaurs, and they are the last of the major groups to evolve. And that's pretty exciting, the kingdoms. Yeah. Okay, so here's your next one. Birds and mammals arise both from reptiles. That is false. I just said that birds are from dinosaurs. Dinosaurs evolved from reptiles. Mammals evolved from reptiles. So it's dinosaurs and mammals that evolved from reptiles. Okay, some more evolutionary milestones, and we're going to talk about these a lot, but I just want to give you a little preview. KT transition, right, the Cretaceous to Tertiary, it begins the age of mammals. It's about 65 million years ago. Mammals become the dominant group, okay? Now, about 6 million years ago, we first start to see the hominids, okay? And actually, it can be longer than that. If you start including the orangutans, it's closer to like 11 million years. But when you start looking at these guys and all of our close relatives, it's about 6 million years. And then Homo sapiens, we show up about 150,000 years ago, and that's one of the things that we're going to be most interested in going further in the course. All right, that is it for today. If you have any questions, please let me know next time, and thanks for listening.